Good evening, everybody. So let us start our lecture this evening. Today is August 26th, right? 2021, and then this will be our fourth lecture in the second week, the last lecture of second week. So as usual, so let us quickly open our syllabus. So there is nothing changed in our syllabus, and then so let us go to our schedule page. So our schedule page, according to our schedule, so we will cover Master Theorem today. We already covered divide and conquer method we discussed in our last lecture. So today we will discuss Master Theorem. So if you go to the book, okay. So on page number, actually in real book maybe page number will be 93, but here in the PDF copy, so there are some extra pages at the beginning, so those are not numbered in the book. So maybe 114 page number. Okay. So everybody, can you see my screen? Do you see my screen? Okay, that's good. You see my screen. So okay. So today just we will learn, at least we will cover only one thing. So Master Theorem. We will understand Master Theorem, and then we will see how do we apply Master Theorem to measure or to calculate running time, that means efficiency of an algorithm. Okay, so Master Theorem is originally it came from mathematics. So this mathematics formula. This formula came from mathematics. So let us understand what is it. In our last lecture, we discussed a little bit about Master Theorem, and maybe I asked you to read. I'm sorry, read this section if you have a time. Okay, so the Master Theorem, it provides a cookbook. That means it's called a template or something, cookbook method or something, a guideline. Okay, method for solving recurrences in the form or of the form. This is the form Tn, time to run an algorithm in terms of n, equal to a times t of n by b plus fn, where a greater or equal to 1 and b greater than 1. These are some constant. Okay, literally a will be an integer number, but b can be a fractional number as well as, and the function fn, that is an asymptotically positive function. Asymptotically positive function means the all the way n for an infinite number, this still it will be in positive coordinate. Coordinate. I will show you using graph soon. Okay. So in Master Theorem, actually we have three cases. In Master Theorem, we have three cases. Case 1, 2, and 3. We will learn these three cases, and then we will see some. We will solve some examples, some problems like this. So if we do this, solve this problem, then we should have a good understanding about Master Theorem. Okay. So if you know the Master Theorem, if you understand Master Theorem, then you will see that you can solve some problems. You can find the running time of some problems just on your head or using or it says without using pencil and paper. And then in a few a few seconds or in a few minutes you can find the running time of an algorithm. Okay, so here 4.20 is described the master theorem. Okay, so as we saw, give me 1 second please, let me turn on the light. I'm sorry, I got cough. So as we saw in our previous 2 lectures that we use divide and conquer method, in mainly we discuss with Marsh-Short algorithm, right? So we divide the problem into some sub problems. Okay, so here A denotes how many sub problems, and this B denotes the size after every time it's dividing. So B, so we know that in Marsh-Short algorithm, we divided every time, we splitted the sub data set or problem every time in half, so that we got 2 sides. Half means 2 sub problems, and then each of the size n by 2, n by b. Okay, so here A and B are positive constraints. So then A sub problems, there will be A sub problems that will be solved recursively, and each will take time t of n by b, because we are splitting by b, dividing by b. So each time there will be A sub problems, and then it will take t of n by b. So total time will be A and t of A into t of b by n. And Fn, it denotes the time that requires for divide and conquer. Both divide, splitting the problem, and combining the result. So no, not divide and conquer. Divide and combine, not conquer. Divide the problem and combining the result. So that time is denoted by Fn. Okay. So in the problem you will be given a real Fn function, a function in terms of n, and you will be given the value of A and B. Then you will be asked to solve this problem to find the running time. Here one thing is that for instance A can be 7, B can be 2, okay, and Fn can be theta of n squared. We will see some examples. So sometime you see that we, in our last lecture we discussed floor and ceiling. Floor means sometimes you may not have even number of data every time. So if you do not have even number of data, so if you split by 2 even, or even in Marsh-Short algorithm, so if you have, for instance, odd number of data, like 15 elements, if you divide by 2, then you get 7.5, right? 7.5, you cannot have 7.5 elements. In one side you will have 7, another side you will have 8. So in general, by t of n by b, we didn't mean either floor or ceiling or both. So that is not a factor. Okay, so now let us see. But for the convenient, we will use this simple, straightforward formula. Okay, so now see that, let us see the master theorem in mathematical format here. This is the definition in mathematics. So let A greater than or equal to 1, B greater than 1 be constant number. Okay, A normally be, I say the A normally be an integer or whole number, and B can be a fractional number as well as either whole number or a fractional number. And fn is a function. Okay, and then Tn b is defined on the non-negative integers by the reference. Okay, so the non, and then Tn be defined on the non-negative integers by the recurrence like this: Tn equal to a of t n by b plus fn, where we know that n by b means either ceiling, either floor or ceiling. If there is something like this, then there are three cases. So there are three cases. Number one, if fn is this part, fn equal to big O of n to the power log with base log of a with base b minus 1. This is not log of a minus epsilon. It is called, we'll read it as log of a with base b minus epsilon. Okay, for some constants epsilon is greater than 0, that is positive constant. Epsilon can be whole number or it can be a decimal number, but it is greater than 0. If we find, because we will be given fn, if our fn is something like this, and if we can find an alpha epsilon value, then Tn will be theta of n to the power log ba. Okay. Now the second one, if fn equal to theta of n to the power, you see that this one, first one is big O, second one is theta, and last one is omega. Okay, when you write in computer, if you cannot type in theta, then you can write theta, theta, plus you can spell out theta. And this is here log a with base b. Actually here minus 0, right? Here epsilon equal to 0. Here you see the epsilon equal to 0 over here. Okay, then we don't need epsilon over here. Then t of n equal to log this part, this is the same part, this part, times log n. And the third case is that if fn equal to lower bound or omega of n log b log a with base b plus epsilon for some constant epsilon greater than 0, and there are also some conditions over here. We will discuss this condition some later. Okay, then Tn will be theta of fn. Okay, so these are the three cases for master theorem. So one thing you may have noticed here, that in all three cases, especially case 1 and 3, we are taking the dominant or the larger part as our running time. So here, let me draw it. Draw something. Okay. And before I forget, so let me explain this one. So what is meant by asymptotically positive? So f1 is an asymptotically positive function. We are familiar with this coordinate system, right? This is 0. For instance, if we say x, and this is y-axis, this is x dash, this is y dash. right? So this quadrant is called first quadrant, that all positive value x, and for this go right side, and all positive value y go on the right side up. So this is called positive for x and y equal to positive. This is the first quadrant. We call this one, sorry, this one, x is the positive value and y is negative value. Okay, this quadrant, any value in this quadrant, it's like x is positive and y negative. And for this one, let us go this one. X is negative, y is positive. And for this one, x negative, y negative. So this is the positive quadrant, right? So a function, we say it asymptotically positive function. That means if a is function, if n is a function, then anyway for any value of it, it will never cross this line. Okay, it will never cross, or never cross this line. Okay, somehow it will be within this coordinate, first coordinate. The function always will lie in this coordinate. It will never go to the other coordinate. That is means asymptotically positive function. That means that the asymptotically for the long run in asymptotic position, this function will lie in the positive quadrant. Okay, this is meant by asymptotically positive function. Okay. Now, has anyone any questions so far? Now let us come with this, the three cases of Master Theorem. Our goal will be to explain these three cases. And if I can help you to understand these three cases in Master Theorem, then I will be happy tonight. This is our goal to learn, okay? This is something, a critical thing, so I like everybody to give attention, okay? And if you have any problem, please speak out, okay? Please let me know if you do not understand at any point, so please let me know. Let me download attendance. Okay. But please raise your voice, okay? If everybody becomes silent, then this class will be something non-interactive. Okay, so let me, so this one, okay, I was discussing this one, right? Let me write it in large font, what I mean by this one. Now, case one, so if case one, let me write it from here, if n equal to, I'm writing in large font, O n log A with base B minus 1. This minus 1 goes here. So after this minus 1 goes like this. This minus 1 is not, it is not like this. N to the power log B A minus 1. This is not like this. This is the correct one. Okay. what we will do is says we will find out this value. We will find out this n to the power log of a with base b. Then we will get a result. We will get a number over here, right? Then we will have, oh, it's epsilon over here. Epsilon. It's epsilon. Then we will subtract epsilon from that. So this is that, this mean. Okay. So here the three cases we discussed. That case 1, if fn equal to big O of n to the power log a with base b minus epsilon for some positive epsilon, then T1 will be theta of n to the power log b of a. So here for case 1 and case 3. Case 3 is that it's minus epsilon and then it's plus epsilon. So if it is plus epsilon, that here Tn equal to theta of Fn. So in both cases, we are considering the dominant part or the larger part, right? The larger value. We are considering n to the power log a with base b, okay, and comparing with Fn. Okay, so we are comparing this, and whatever is greater, we have a sign over here. The sign can be greater than or less than. Okay, so it can be less than or it can be greater than. So whatever is dominant value, so whatever is greater than, we are having that as our result. So in case you say log n to the power log b of n minus epsilon, that means this one is the dominant. Whenever we see minus epsilon, in this case, I'll write it here. So for case 1, this is the larger. For case 1, this is the larger for case 1. Okay, so this is why we are having running time is this part. But case 3, that means Fn equal to this plus something. That means Fn is the larger. Fn is larger between these two. So then the result is theta of Fn. Okay, so that means in all cases, and for this one case 2, here epsilon equal to 0. Right, it's epsilon equal to 0, a minus 0. I can say epsilon equal to 0. So if it is the case like case 2, then we need this on this one, and then plus times that means multiply by log n, LGN. This multiplication sign over here. Okay, so that means what I wanted to say, that for both cases we are getting the larger or dominant part, either this or this, as our result. Now I will go this with some examples. In the example, you will be given value of a and b and Fn. This value will be given, and based on this value, a given value, you have to find epsilon. You have to find a value of epsilon, and then based on the value, based on this comparison, we will find that our given equation or problem will fall either of these three cases, one of these three cases. Okay, and one more thing, that it is not likely that for all problems will can be solved using recursive using Master Theorem, but most, but not all. Okay, because there are some gaps between 1 and 2, the case 1 and 2, and case 2 and 3. Okay, we will discuss those gaps also. Okay. Now, so far, has anyone any questions so far? So I like you to give attention, because as our tonight's goal will be understanding Master Theorem. And if you understand Master Theorem, and if you can solve some problems using Master Theorem, then we will be happy. Okay. So now that last thing I told, that not every problem can be solved using Master Theorem, but most. We'll see there are some cases here. So note that the three above cases do not cover all possibilities for Fn. For any Fn function, it cannot be used. So there is a gap between 1 and 2 when Fn is smaller than this one, but not polynomically smaller. Okay, polynomically smaller means if you have polynomial function. For instance, x to the x squared, x cubed, x3, x to the power 5 something in Fn. Okay. And similarly, there is a gap between case 2 and 3 when Fn is larger than this, but not polynomically larger. Okay. So I will discuss that what is meant by polynomically larger at the end. Okay. So if the function Fn falls into one of these gaps, then or if the regularity condition in case 3 fails to hold, then we cannot. So the regularity condition for case 3 is here. The additional condition for case 3. Okay, this is the additional condition is case 3. If that falls, if that regulatory condition is fails to hold, then we cannot use the Master Theorem to solve the recurrence. Okay. Now let us see some real problems, some actual problem. Let us solve this. Then hopefully we will understand Master Theorem. Okay. So we have 5, 6, 7 problems. Let us solve this. Okay. At this point, has anyone any question? So if you have any question, please raise your voice, okay, and let me know. Really, this is a difficult task and this is a confusing task, but so I'm going slowly so that you understand. Now for the next 10 minutes, everybody please give attention. Okay. Our our first problem is given as here. So that is the problem. Use the Master Theorem. Okay. So this is our topic now. To use the Master Theorem, we simply determine which case, if any, of the Master Theorem applies and write down the answer. If we find any of the 3 cases, then easy to find the answer. So number 1, problem 1. This is problem 1. Here, problem 1 is Tn equal to 9 T n by 3 plus n. So here a equal to 9. So a equal to 9. Oh, we are given already. I don't need to write down, but we can underline. So here a equal to 9, right? A equal to 9. B equal to 3. B equal to 3. And fn equal to n. And fn equal to, this is the fn equal to n. Okay. So what do we have? N to the power log b of a. So equal to n to the power log b equal to 3 and a equal to 9. Okay, equal to theta of n squared. That means n to the power log base 3 and the 9, right, equal to, we can write n to the power log 3 and 3 squared, then equal to 2. 2 will come here, n to the power 2 into, we can say, log 3 of with base 3. So this value is 1, right, equal to n to the power 2 8 to 1, 2 times 1 equal to n squared. So this is n squared, theta n equal to n squared. So now if we compare with this, fn equal to, so if we have epsilon equal to 1, if we take epsilon equal to 1, then if we say epsilon equal to 1, then this one, okay, this one, this part will be theta of n, 2 minus 1, right? Then it will have, this one will be theta of n squared minus 1. This is our epsilon value that I said that we need to find out this first. Then we will subtract this epsilon. So if we put epsilon equal to 1, then it gets theta or big O, whatever you say, n to the power 1. And that is our function. Fn equal to, this is our function, fn equal to n, right? So then we got n over here, we got same function. So in that case, so what is the result over here? So the result Tn, then so Tn will be, so Tn will be theta of this, theta of this, theta of this. So what is this? This value? N squared. Okay. Theta of n log 3 by 9 equal to, we say theta of n, we got this one, 2. Okay. So in that case, what is the solution? The solution is Tn equal to theta n squared. Okay, so Tn equal to theta n squared. So this is like, so Tn equal to theta of n squared. So here in this case, we see that case 1, it fall into case 1. Okay, now do you have any question?
Hello. Yeah, I had a question.
Yes.
Where did you get the epsilon value that equaled 1?
So if we at this case, in this case, we see that if we have epsilon, if we think that epsilon equal to 0, if we let epsilon equal to 1, sorry, not 0, then we get this, right? So epsilon, if so, we in the formula. So let us go back to the case. It says for some constant epsilon equal to 1, for any constant, or we can say if we find any epsilon value. Okay, so in that case that we have epsilon 1, if we consider epsilon equal to 1, then we can find that this will be this one will be equal to Fn, right? It's easy to see, like, so because this one, what do we find here? This one, what do we find here? This one here, we got, let me write it down again. We got here, so our condition is that we said if we find Fn equal to big O of n to the power log A with base B minus epsilon, we will check whether we have a value of epsilon, if there exists any epsilon. So in case here we see that, okay, you see that if we put epsilon equal to 0, 1, epsilon equal to 1. So if we put epsilon equal to 1, then we see that, then we find that, then we find that if n equal to, what is Fn value? N equal to big O of n. So this one is 2, right? B equal to 2, then let me write it down again. Log 3 of 9, log 9 with base 3 minus 1. So that what is here? So here big O of n to the power 2 minus 1. So that means big O of n to the power 1. 2 minus 1, that is 1, right? So that is Fn. And Fn is here, n. Fn equal to n. And big O n, or it's a theta of n, so that is a constant. This is the same function, right? So then you can say big O n or n over here. So this is function Fn equal to n, and this is also n. We got the same thing, right? So for epsilon equal to 1, we get this. So that's so it falls into case 1. And according to case 1, what is the dominant part over here? So this part is dominant, right? So this part is dominant. This part is dominant. Okay. So maybe you do not see over here. This is squared over here. This squared. I'm not sure why this is a line coming. This is a box coming from my stylus. Let me move it a little bit. Okay. Let me erase my handwriting so then you can see, or you can see here, Tn equal to theta of n squared. Now, do you understand? I think if we go one more example, then it will be clear. Let me go to the next example. Then I think it should be clear. Then this is our next problem. Our next problem, P2. I'm sorry, my pen. Okay. Our next problem, P2, is this. Problem P2. Tn equal to 3 t of n by 4 plus n log n. So this is our fn equal to n log n, fn equal to n log n, and a equal to 3, b equal to 4. Right? It's easy. So here now we see that n log b a equal to n log, what is b value here? 4. Right? And what is a value here? 3. Okay, so we know that log a or base a equal to 1. So if this is 4, then the result would be 1. So but this is 3, so result would be something smaller than 1. So this is why with calculator they find that 0.793. Okay, so approximately 0.8, right? So that is big O, then n to the power 0.8 something. Okay, or 0.8. What do you say, right? 0.8 or sorry, 0.8. So this is 0.8. So now if we think that now it is 0.8, okay, so it is less than 1, right? It is less than 1. Now if we consider epsilon equal to 0.2, okay, then actually it does not apply into recursion, so I think it is not a good example for us at this point. Apparently it seems to be that if we put epsilon equal to 0.2, it falls in cases 3, but not. Okay, so then even let us see, if epsilon equal to 0.2, so then what is this part? We add up 0.8, then we will get theta of a big O of or n to the power 0.8 plus 0.2 equal to 1. That is big O of n. But our fn, what is that function? N log n, right? Fn or n log n. But this part we are getting n. So we are comparing these two methods. One side is n and another side is n log n. So n log n. Okay. So for all n value, this comparison does not become stable. For instance, for value of 1, if n equal to 1, so what do we see this side? N equal to 1, and this side n equal to 1 times log 1 equal to 0. So then this part will be 0 for n equal to 1. So that means this part is dominant, larger. But for larger n, okay, for instance n equal to 100, 1012. Okay, in that case, this part will be dominant. Okay, so that we see that this condition either greater than or less than does not persist. This is why this falls within the gap. We say that there is a gap between 2 and 3. So this is within the gap, so it does not, we say the master method does not apply for the recurrence. So but let us go to another example that we see that it applies. I think they will be easy to understand. So do you have any question for this part? So master theorem, it does not apply because for some n this condition does not persist. For some n this part will be greater, for some n this part will be greater. Okay, so that means it's not stable, so that master theorem cannot be applied for this part. Let us go with another example. Okay, I think let us go with another example, then we see the word critical. Okay. Case 2. Number this one. Let us see this one. So this problem. For this one, we have so Tn equal to 8 T of n by 2 plus theta of n squared. So what is our A value here? A equal to 8, B equal to 2, and then Fn equal to theta of n squared. Okay, so here if we calculate n to the power log of b, log of a with base b equal to n to the power log of 8 with base 2 equal to n to the power, we know that the 2 to the power 3 equal to 8. That means it will be here log 2 to the power 3. That means 3 will come here. That means we will see this one n to the power 3. So here Fn equal to, we got, so here we got this one equal to n to the power 3. So we got this one equal to n to the power 3. Now f of n, according to our formula master theorem case 1, f1 equal to big O of n to the power 3, this one n to the power, let me write it down, log of a with base b minus epsilon equal to big O of n to the power 3 minus epsilon. So here. So now in this formula, is there any epsilon, positive epsilon value exist for which Fn, this one will be equal, Fn will be the same thing. F1 will be this value. This value will be equal to Fn. Yes, we see that if we have here epsilon equal to 1. So here if epsilon equal to 1, then we see that right side n to the power 3 minus 1 equal to n to the power 2. That is equal to our this function, Fn function, right? So we see that, say that for epsilon equal to 1, we get that this part for epsilon equal to 1, Fn equal to this one. So here that means it falls into case 1, and according to case 1, this running time will be, which one is the dominant part, this one or this one, n squared or n cubed. So that means we have one side n cubed and we have another n squared. For any value n, so for instance, for n equal to 1, this side equal to 1, this side equal to 1. For n equal to 2, this side will be 8 and this side will be 4. For n equal to 3, this side will be 27 and this side will be 9. So always this part is dominant, right? N cube is always greater than n squared. So that means it does not fall into any gap, but it falls into case 1. So the running time will be theta of n cubed, not theta of n squared. So theta of n cubed will be our running time. Do you understand this one? Has anyone any question? Okay. Now let us go, if you don't have any question, let us go to the next example. Here, in this case, here in this problem, here a equal to 7, b equal to 2, and fn equal to theta of n squared. So that's n to the power log a with base b equal to n to the power 2 to n to the power 7 with, or log 7 with base 2. So we know that log 7, it will be, if it is log 8, log 2 base 8 will be 3. Log 2 to the power 3, 2 to the power 3 equal to 8, right? Equal to 3. So that it is 7. So its value is something less than 3. So this value will be something less than 3. Less than 3. Okay, so that means 2.81. They got 2.8 or 2.81. Okay, for instance, 2.8. Okay, so now we got this part. Okay, so then here fn equal to big O of n. What is log 7 with base 2? This is base 2. This is why they did not write 2 over here. So we got 2.8 maybe 2.8 for instance 2.8, and then if we have minus epsilon. Okay, now if we consider epsilon equal to 0.8, now if we assume that epsilon equal to 0.8, then Fn will be big O of n to the power 2.8 minus 8 equal to n squared. Then we get this one equal to our n squared function, equal, right? So that means it falls into case 1, and then running time will be, what is the running time here? The dominant part. What is the dominant part over here? This one. Running time will be, so the running time will be log theta of n to the power, you can say 2.8, or you can say log 7. You see that here, so it has log 7. So dominant part, this part, you can say either you can say 2.8, or the dominant part is the so now do you understand case 1? Has anyone any question?
Yes, sir. With the problem we just did, with the T of 7T, why is it 8 throughout the problem? Or am I just missing a?
Which one? Which line?
It's Kyson.
Sorry?
I was talking about for T of n equals 7T for the problem beginning. When we was doing
This
it,
problem,
everything was log.
this problem or up? This problem?
Yes.
Okay. Tn equal to what?
I was assuming that was the problem we were doing, and I saw it was log 2 of 8, and I thought it would be log 2 of 7.
This one, Tn equal to 7 times T 7 n by 2 plus theta of n squared. This is our original problem. So what is your problem? Which part did you not understand?
I think I was just confused on which problem we were doing.
Now you understand?
Because I would assume
here A equal to 7, right? B equal to what?
B would be 2.
2. And then Fn equal to?
N squared.
Huh?
Okay.
What's the value? Theta of n squared.
Yeah.
This part is Fn. This part is T. This part is B, and this part is A.
Okay.
So then here we calculated here log. So we calculated here. So last I calculated the top part, not the n to the power. So here log of B and A, okay, equal to this one. B value equal to 2 and A value okay, so here actually I considered actually I said if B equal to 8, if A would be 8, then we would get 3. But since A equal to 7, so we are getting values something less than 3. This is why they got something less than, yeah, this value equal to 2.8. Is that a confusing part?
Yes, sir.
Okay, so actually I said if we would have A equal to 8 instead of 7. If we would have A equal to 8, then we would get 3, right? This part would get 3, right? This part would get 3.
Yes, sir.
Okay, but we have this A value. We have a value 7. So we will get this value something less than 3. Less than 3. So that we got here the calculation, they did the actual calculation, they got 2.8. 2.8 is less than 3, right?
Yeah.
Okay, sorry, I did not, I spoke that out, but I did not write it down. Okay. Well, what I can do, I can write it with 7. Okay. Okay. 7. 7. Then we will not be confused. 7. Then 7 equal to, if it is 8, so my calculation is easy, so that like hand calculation, okay, without any piece of paper. So we discussed that if we know the formula technique, we can solve this problem in our head without any piece of paper. So this is how my calculation was that sometimes if I would have 8, then I would get 3. Since this value is less than 8, so my value result will be something less than 3. So that they got something less than that, they got 2.81, then 2.8. I do 2.8. Whatever 2.8 and 2.81 is almost same, right? For this case. Even if I put 2.81, then in that case, epsilon is equal to 2.81. Okay, now you understand?
Yes, sir.
Okay, we have a few more minutes and we have a few more problems. Let us go with this. For this one, let us go to this one, this problem. For this one. Okay, this problem. Here, a equal to 1, right? This problem. Here, a equal to 1. There's nothing means 1. And b equal to, what is the b value? 3 by 2. Don't be confused over here. Not 2 by 3, because our something like this. Here Tn, let me write Tn equal to 1 times T of n divided by 3 by 2 plus 1. I'm sorry. So now we understand that. So then this 2 will go up. This is the 2n by 3, right? So then b equal to 2 by 3 by 2 and fn equal to 1. Fn is a constant function over here. Now into the power, they did a calculation, log of a with base b equal to n to the power log of 1 with base 3 by 2. Okay, and we know that anything log 1 equal to 0 with any base, right? So this part we know that log 1 equal to 0. We know that log a with any base, a is any base, log 1 equal to 0. If you remember your high school math, log 1 equal to 0. That means n to the power 0 and then equal to 1, right? So here we got exact mass, this one with our fn. So that means here epsilon, here, epsilon equal to 0. We do not need any epsilon value. Here epsilon equal to 0. So then it falls into case 2. So according to the case 2, okay, according to the case 2, what is our result? Tn will be, according to our case 2, our result will be, then T1 will be theta of this part and log of A or B into log n. So we know that this part equal to 1, equal to theta of this part equal to 1 into log n equal to theta of log n. Do you understand this part? This one? Do you understand this? So your assignment and in some quizzes and your test, you will be given some problems like this. Okay. And then you have to do your calculation, show your calculation. You have to show your calculation to find the value of Tn. So there is a common pitfall over here that people do mistake in finding B value over here. So A is easily findable, but B value over here. So here in this case, it says 2n by 3. That means we need to organize this way. That actually B equal to 3 by 2, not 2 by 3. Okay. Has anyone any question? Okay, so there are a few more examples or few more problems over here. See that? Please do this. Solve these problems. Okay, you will get some quiz questions from this section. And if you want to see the and to understand the proof of Master Theorem, you need to read this. And there is a Master Theorem, explanation Master Theorem for exact powers. Okay. And there is a lemma that this is a mathematical thing. We don't want to go here. Okay. So has anyone any question about Master Theorem and how do we apply Master Theorem to find Tn, running time of an algorithm, that means of an expression? Has anyone any question? Okay, if you don't have any question, then thank you so much. Thank you for joining. And let me see. I am going to upload the lecture videos. So this is your section. Okay, so the videos that I have uploaded, lecture 1, 2. Okay, these 2 will be going here. I will manage it. 2, 3, and then tonight's video will be lecture 4. Okay, thank you everybody. Thank you so much. hope I will feel better, and then I will hope to see you next week.